Hello and welcome to Learn Data. It's great to have you on this channel. In this video, we'll look at another exciting project, which is to do with separating audio components from a mixed audio. So briefly, I'll give you a brief overview and then we'll do the actual coding. So if you remember from previous video, we looked at this example where we have this audio signal which has three different mixed audio sources in it, and what independent component analysis can do then is separate out each of those components, as we can see here on the right hand side. So the project for the data for this project are these four wave files that you can download it. I'll put the link for the files in the description of this video. So let's get started in Jupyter Notebook. If you are planning to create your own data set, here's one way to do it is you can put a microphone in a room, and I probably want to record it when it's quiet and there are no background sounds. You can simultaneously play three different sounds. One could be, say, cell phone ringing, one could be yourself talking, and then the third sound could be keyboard sound. Or alternatively, you can use software such as Audacity, which is again free and open source. And in that, you can mix three different tracks to create a mixed audio track. We want a couple of these. So in this example, we are using four. About should be at least maybe 15 seconds up to a minute long. Should do. And if you want to use the data that I've created, here I'll put the link, complete link, from where you can download the data. So let's get started. Here are the libraries that we'll be needing. We have NumPy, Matplotlib, and then from Scikit-learn, we're going to import decomposition. Then we have the wave, which is the scipy.io, and then again we have wave and the OS libraries. So the first thing that we'll do here is set up the path. So we have path is equal to this is on my computer, so the path on your computer would be different. Desktop, and we have Python on projects, ICA underscore audio. And I tried several different examples, so this was the example 2 that I'm showing here. Okay, so the first thing that we'll do now is read the files. We'll read the audio files and put them in a dictionary. So to do that, let's say we create heading here, read audio files, and so here now we'll create a dictionary dwave as an empty dictionary, and then we'll loop through all the files. So for file in os.list dir path, so we get that, and then just in case if that directory has other folders and we want to avoid those, then we can type if os.path.is file os.path.join path file. So this is just to get only files in the directory, to get only files in directory and not the folders. So we'll get the f name. So file name is equal to file.split, and we'll split it on the dot and get the first part. So we just need the name in fname, and then for the extension file.split. And the reason why I'm doing this is because if you have mp3 files or other extension files in the same folder, which you probably won't have, but if you have them in that folder, then this will take care of that. If f extension is equal to wave and file 0 file 0 is equal to s, that should be equal to s, and length f name 4, then you want to do is d wave f name is equal to wave dot open, and then we have path plus file, and then sorry, R for read. Okay, and finally we can look at the keys. So d wave dot keys, and okay, so we run that. OS is not defined. I wonder why. We have imported the file. This okay. So this is length. I missed a bracket there. Okay, so these are the dictionary keys S1, S2, and S3. So we have successfully read the mixed audio files. Now what we'll do is uh, we'll go on to the next step and create another dictionary signal. So we'll get the signal out. So get signal, and again on this the markdown cell. Okay, we one more hash there. All right. So d signal is equal to open close braces, and then for key in the wave dot keys, temp is equal to the wave key dot read frames, and here we put a -1 d signal, and you have the key is equal to np dot from buffer temp, then converting it to integer in 16. Okay, so next, then we are now ready to plot these. So before we do that, we need to get the timing and the frame rate. So get timing and frame rate. So this is another heading, and here we can specify fs is equal to d wave s1. So we can get all of that from the audio track s1. Get frame rate, and then similarly for timing, can get it for in space 0, and then length d signal s1, and okay, so this divided by fs, that is the frame rate, and the next is number is equal to length d signal, and again s1. So we run that, and now we can plot these. So let's see how it looks. Now for plotting, uh, can we can simply use the plt.figure and plot plt.figure big size is equal to 12 by 2, and plt.title, this is the original, this is the S1 that we are working with, and plt.plot timing the signal S1, and then we have the color here, so it could be any color. This should be in a tuple. Okay, so that's how the audio signal S1 looks like. What we'll do next is we'll plot all of them together. So we can do that in a for loop, and for that we'll use CMap to uh, put list of colors in there. So plt.cm.rainbow np.linspace 0, 1, length the signal. So that gets us the color, and then we have for key and color in zip the signal.keys and color, and now we can actually we could have copied. Let's do that. I'll copy this, paste it here, undo, cut, or put a tab there. Title I usually prefer to write the very fast. Okay, so we have this, and then uh, plot timing designal, and here instead of S1 we can specify just the key, and here we can specify the color is equal to C, and for title we can specify key, and then we can say plt.show and then run this. So as you can see, these are the 4 different tracks that we'll be working with, S1, S2, S3, and S4. The job now is to find the individual components. So we train the model on these 4 tracks and extract our uh, individual sounds. So to do that, now if you are wondering how these tracks sound, let me show you how they sound. So we can actually write a code in here as well to play the audio, Jupyter notebook. Alternatively, we can uh, play them outside of Jupyter notebook, so either of those two is fine. To play the audio, we'll import the IPython library. Import IPython.display as IPD, and we can specify IPD.audio audio. Then here we specify the file path plus s1.wave, and when we run this, should get a play button. I don't know if you'll be able to hear this, but here is how this particular audio would sound. 1, 2, 3, 4, 5, 6, 7, 8, so 9, how the audio 0, sounds. 1, maybe it will be much more clearer if you listen to the audio 5, directly 6, on your computer. 7, 8, 9, so 0. With that, then we can move on to the next step, which is we create a matrix. So let's do that. Create matrix, and for this again we'll use the for loop. So we'll create an empty list X, and within this we'll put all the numbers in form of a tuple. So rather than matrix, we'll just get dataset. Okay, So here then we have for I in range length d signal, and within this we are going to use the list. What we want are the length of the values in each of those. So that's why we are going to do it this way. List. So we have d signal, and then we have list, and within this we need the signal dot keys, that. Then here we need, this is the first 0 component, and then that should work. Okay, and then we can initialize temp, another list, and then for key in sorted d signal dot keys. Here we have temp dot append d signal dot d signal, and then we have key, and we have I, and here we have x dot append tuple temp, and now we can print length x and length, so we have another length x here, and we can also print the 10 values from this. So starting from 0 to 10, run this, should get a list x created, and then within this particular list we have these components. So these are the components from track 1, track 2, track 3, track 4, and those are now in here, which will input to the model. So the next step is fit the model. So here we have fit model, and we are going to use the FastICA from Scikit-learn. So model is equal to decomposition.FastICA n underscore components is equal to 3, because we know ahead of time that there are 3 sources of audio in each of those tracks. Model.fit x, and then x ICA is equal to model.transform x, and then we can finally print of what it looks like. So x underscore ICA dot shape and x underscore ICA dot shape. So when we run this, we what we are getting is the transformed audio that was learned by this model. So print XICA. String has no attribute XICA, because this should be a comma. And after this, we can then separate out the tracks for plotting. So once we get this done, okay, so this is good. So we have 3 tracks in the output. That's the length of each track. Now what we'll do is get the separated track. So get separated tracks sources, rather than tracks, such as sources, and we'll put that in another dictionary, which is DICA, and for I in range x underscore ICA dot shape 1 and DICA I is equal to x underscore ICA, and here we specify I. So when we run this, we now have, so if we look at the dictionary, we have each track has a separate key there. Now what we'll do is plot these. And so for plotting, so plot the sources, and so again we can use the exact same setup that we had earlier for this. Let me just go ahead and copy it, paste it here, and what we need to change is the dictionary name. So instead of D signal, we now have DICA, and for title we can say this is signal number plus string key. And for plotting we have timing, and here we have DICA and key, and the color is on the same C. So when we run this, we should be able to see the three different signals, and these are the signals. So let's try playing them. So I'm going to copy this and put this right here. And now what we can try playing is maybe the signal 1. So this is not a wave file. So what we need to do first is save these as wave files. So to do that, dout is equal to, so let's put a heading there, save audio, dout is equal to that, and then for key in dica.keys, and then dout key is equal to np dot int, so integer dica dot, sorry, dica key, and then we'll multiplied by 3 to 767 to get the audio. And finally we'll write this. So for key in d out dot keys wave file dot write, and then we can specify the path plus we have out underscore signal underscore, and then string key, and then we have plus dot wave, and for that we have fs and dout, and then we have the key. So with this, the file should be saved in your directory, and then we can try playing this. So play audio. So here we can specify ipd dot audio, and then you have the path plus the first file would be out underscore signal underscore 0 dot wave, and then similarly we have the other two files. So this would be 1, and then the next one would be 2. So if we run this, we should get the 3 play buttons. And now I'll try to put the headphones on the mic and see if it can record the audio. So this is the first track that was separated. And then this is the second one. And then this is the last one. So if you play these on your computer, I think you'll get a better audio quality. Uh, so as you probably have seen, this particular, which is the singing ball sound, that's pretty good separated. The sound from the wooden ruler, that's also good. The audio is bit uh, stressed out, uh, but at least we do not have the other two sounds in the background with that. So that's a positive side of that. So that was it for this video. Then I hope you enjoyed this project. I hope you get a chance to run this on audio files that you create on your own and see if you can separate this using the same code. The care you want to take is you do not want to have multiple sounds in there. So if you just limit yourself to 3 tracks, for example, if you take audio of a traffic, then in traffic there are horns, there are sounds of wheels, cars. So there are too many sounds in there. What you want to do is restrict and limit those sounds only to just a few, and then put those as number of components in the model to extract that and those sources out. If you have any comments or suggestions, please let me know in the comment section below. I hope to see you all in the next video. Please like, share, and subscribe. Thank you.